Principal component analysis is one of the oldest techniques in machine learning. It dates back to the work of Eckhart and Young in 1936, but solutions to this problem have existed even earlier from the work of Beltrami and Jordan in the 1800s. It deals with the problem of finding low-dimensional structure in high-dimensional data, particularly fitting a low-dimensional subspace of dimension D to data drawn from a space of ambient dimension capital D. In many applications, however, the data is corrupted, and there are many data points that might lie outside the given low-dimensional subspace S. And so this is denoted here, where you've got the blue points that lie in the low-dimensional subspace little s. But then you've got the red points that are the outliers. And therefore, what you are given is a data matrix X tilde that is composed of both inliers X and outliers O. And then there is an unknown permutation gamma. And that is because you don't know which point is an inlier and which point is an outlier. Now, you could use the same classical subspace fitting solutions based on the singular value decomposition applied to X tilde. But the SVD is well known to be not robust. Yes?
So do you move your slides?
Yes, I did.
But here we didn't. Yeah, so I didn't say moving slide.
Okay.
Could you try that again?
Do you see the slides now?
Yes, so I'm seeing the second or third slides, yes.
Okay, so now do you see them in full screen?
Yes, can you try to move or?
Are they moving now?
No.
No, that's very strange. Let me stop the share again. Let me put it in full screen mode first. Wow, that's interesting. Let me just close Keynote and restart it then. Okay. Let me maybe just share my full screen then. What about now? Are they moving?
Let me see. Now it's in the second slide. So can you try to move?
Yeah, I've been moving.
No, we are still.
No.
Okay, so now we are jumping to the first slide, to the title.
Okay. So there's maybe just a delay then.
Okay, can you move now?
Yes.
Yeah, okay, it's moving. Yeah, right. Okay, yeah. Good.
Okay, great. Thank you.
Okay, yeah, thank you.
Okay. So this question of fitting a subspace to data corrupted by outliers has a long history, and there's been many works that have tried to address this issue, that the SVD is not very robust to outliers. One method that is very commonly used in computer vision is this RANSAC, that stands for random sampling and consensus. And as the name suggests, you alternate between random sampling and consensus. So you sample, in this case, let's say this is fitting a plane, you sample two points. Let's say you are unlucky and you sample 2 red points, and then you fit the subspace to those 2 red points and the origin. And it's not going to have a lot of support. It's not going to have many other points that pass through that hypothetical plane. But if you keep sampling, eventually you will sample 2 blue points, and then you will identify the yellow subspace in this particular case. And so when does this work, and how many iterations do I need in order to identify the correct subspace? Well, this works well if the dimension of the subspace is small, but also if the percentage of outliers is small. But it's well known that this method fails as soon as the dimension is high or the number of outliers is high. This motivated around 2010 many methods based on sparsity, low rank minimization, and various mixed norms. And this method called outlier pursuit was introduced around 2010. And it was very elegant, very nice. Unlike Ransack, it was based on a principal optimization technique. It was, you could have provable guarantees of global optimality for this convex problem. And moreover, you could have very rigorous results about when is it the case that the global optimum, in this case, L is supposed to be the low rank matrix, and E is supposed to be the matrix of outliers. You could have conditions under which the global optimum is low rank, and therefore you identify correctly the correct subspace. And those conditions, again, required the dimension little d of the subspace to be small relative to the ambient dimension, capital D. And similarly, the percentage of outliers, the outlier to inlier ratio to be small. There's been many other methods based on L1 minimization with similar properties. And one that we didn't know at the time we developed our work, but it's actually quite relevant because it's probably the most closely related, is this method called RPCA, developed by Lerman's group at the University of Minnesota, where you try to solve, again, an mixed norm problem. P here is a projection matrix onto the subspace. X is the data, and you try to search for projection matrices. And the constraints that you see at the bottom right are a convex relaxation of the set of projection matrices. But again, the theoretical analysis of these methods requires the dimension of the subspace to be small relative to the ambient dimension and the percentage of outliers to be small. Just to illustrate that more concretely, look at this plot. So the x-axis is the outlier ratio, and the y-axis is the relative dimension of the subspace. Here is synthetic data, ambient dimension is 30, number of hidden layers is 300. So the y-axis ranging from 0.03 is 3% to 97%. You know, roughly the dimension is moving from 1 to 29 in this particular case. White means that the method succeeded at perfectly recovering the true subspace, and black means that it failed. And so you can see a clear phase transition here. And you can see that as soon as the dimension of the subspace is large or the outlier ratio is large, the method fails. This L2-1, the outlier pursuit method, does a little bit better, but still the same behavior. The self-expressive method does about the same. RPCA does clearly better. But regardless, all methods fail in this high or relative high dimension regime. For example, the case of planes or the case of hyperplanes. And what I'm going to be describing today is this method called dual principal component pursuit that is now illustrated at the center. And this method is one of the few methods that currently exist. In fact, I'm not aware of any other one that is able to perform very well in most cases, and in particular in this high relative dimension regime. And why is this high relative dimension regime important? It is important because there are many applications in vision, for example, where you are given point cloud data and you want to fit a collection of planes to the data. This is particularly the case in indoor environments where you want to do a 3D reconstruction, say, of your house. This is also the case in many geometric problems in computer vision, where if you want to match two images, or maybe you want to match multiple images and then do a 3D reconstruction, then you end up, in the first example, you really needed to fit a two-dimensional plane in R3. In the case of two views of an image, if you want to fit a geometric transformation between the two, like a homography, you need to do 8-dimensional subspaces in R9, or if it is 3 views, it may be 26-dimensional subspaces in R27. So that's why hyperplanes tend to show up a lot in these geometric problems. This is also true in systems identification and controls, where you're trying to identify, say, an autoregressive model for a time series. Again, this can be seen as a hyperplane. And well, this is more speculative, although we've seen ample experience of that in our lab in trying to take deep representations from, say, the ImageNet dataset and looking at the rank of the embedded representations that are learned. And they tend to be, let's say, if your latent representation is 4,096 dimensional, maybe these intermediate representations might be 4,000 dimensional. So it appears to be the case that the dimension of the subspaces might be higher than usual for these deep representations. So over the last several years, we've been working on various aspects of this problem. You see here at the bottom, and I'll explain in detail where this problem comes from and why this is an adequate formulation for the problem. But here B represents a normal to a hyperplane that we're trying to learn. And as you can see, the optimization problem is extremely straightforward. We're trying to find a normal vector to the data x tilde, and B, the norm of B is equal to 1. It's just a constraint to enforce that it's unit norm. And so what we've been working on is really trying to demonstrate that this formulation is adequate for the problem. And so the kinds of questions you want to study are, what is the global minimum to this problem? And is the global minimum a true normal to the correct subspace despite the outliers? And what percentage of outliers can you tolerate? And so that's what we call geometric analysis. We've also worked on doing probabilistic analysis. So the probabilistic analysis means typically that you assume that the data is sampled from, the subspace is sampled at random, the outliers are sampled at random. And now you've asked the question, is the global minimum to this problem equal to the true normal with high probability? And what percentage of outliers can you tolerate? And the type of analysis I'll be showing is that you can tolerate a very large number of outliers relative to all other methods. Particularly, as you can see here, the number of outliers is on the order of the square of the number of inliers, which is a very high number. Beyond just understanding the landscape of this non-convex optimization problem, we've also been trying to understand algorithms. Several years ago, and the algorithms are, by the way, almost all of them are relatively well known in general, but their application to this specific problem is what matters here. The first one is ALP, alternating linear programs. And it's one for which we can prove that it converges in a finite number of iterations, in fact. But it's not very scalable because you need to solve linear programs. Then you can do Reweighted least squares, a well-known technique, and that is way faster, but we don't have theoretical guarantees yet, and I think that's a great avenue for future research. We, surprisingly, and maybe as common in deep learning these days, have converged to maybe the simplest possible method at the end of the day, which is just compute the gradient or the subgradient and project it onto the sphere. And for that, we've been able to show that it's both scalable as well as we've developed the theory where we can have guarantees of convergence to the global minimum. And it's very efficient, as you will see. Everything I've said so far is primarily focused on hyperplanes, but we've actually extended the theory beyond just hyperplanes, and I'm not going to talk about it today. So one extension is, what if you have subspaces of higher codimension? And everything I said has pretty much been extended. The other one is, what if you want to do subspace clustering as well as subspace estimation? And we also have been able to show that this Riemannian subgradient method is both have geometric guarantees, probabilistic guarantees, it can handle noise, and the algorithms are provably convergent and scalable. All right, so with that in mind, this is the outline for my talk. I'll focus primarily on hyperplanes today, though, as I said, the theory extends. And I'll present geometric analysis, characterization of the critical points and global minima, a probabilistic analysis that result about the fact that we can tolerate the square of the number of inliers as outliers. Then I'll briefly just define what the algorithms are, but primarily concentrate on the theoretical guarantees of convergence. And then I'll show you applications in 3D computer vision, particularly 3D plane estimation in the Kitty dataset. All right, so let me begin with the technical part of the talk. So just to introduce the notation that I've already mentioned, So capital D here denotes the ambient dimension of the data, capital N is the number of inliers, and capital M is the number of outliers. X is the matrix of inliers, O is the matrix of outliers. And by and large, we're going to be using this matrix X tilde throughout, which is the given data matrix. And the goal is to decompose the given X tilde matrix into the inlier part and the outlier part, and then to actually fit a subspace to the inliers. So in the hyperplane case, we're going to be working with a normal vector B of dimension capital D, and the dot product between the normal vector and the data points should ideally be 0 if you're an inlier and non-zero otherwise. And so this matrix of dot products, in a sense, is B is normalized. In a sense, it's almost like the distance from the point to the subspace, if you wish. And so the natural intuitive formulation, it's really to every time that this vector X tilde transpose B is non-zero, right? If B was the true normal to the subspace, every time that this dot product is non-zero, you would have an outlier. And so this L0 norm of that vector is really the number of outliers, or at least when B is the true vector. So the formulation here simply is find a normal vector B that contains as many inliers as possible, or in other words, minimize the number of outliers here. And B at this level, because the L0 norm doesn't depend on the scale, all we need is B to be non-zero at this level. But anyhow, another way to just write this down is what I've written here. This is just, again, counting the number of times or the number of points whose distance to the hyperplane is non-zero. And we are just going to enforce the norm of B to be 1, just to prevent the degenerate solution B equals 0. And as commonly done with L0's semi-norm, we'll substitute it by the L1 norm. And so that leads to a problem that is L1 minimization like, but it's non-convex actually. And the only reason it's non-convex is because of the spherical constraint that B needs to have unit norm. And so this is DPCP, is a non-smooth, non-convex optimization problem to find a normal to the hyperplane. So as you can see, it's extremely simple, and you would think pretty much well studied in general. I don't have the citation here, but in the early 70 different problems. So I think here the insight is to be able to use these for robust hyperplane estimation. Okay, so the objective function, this L1 norm, can be decomposed as the sum of the errors on the inliers plus the sum of the errors in the outliers. And in order to do the geometric analysis, we are going to introduce a number of geometric quantities that characterize the geometry of the problem. So the first one is what is the minimum error that can be made on the inlier term alone. But notice the B vector is not let to be free, is not any vector in the ambient sphere, but rather is a vector that is constrained to lie on the subspace. So in other words, you're kind of trying to find whether there is a vector in the subspace that fits the data very well. And that's what the CX mean measures. And so here is one extreme situation where the true subspace is, say, two-dimensional, but the data happens to be badly distributed in that subspace. And so in this case, CX mean is 0 because you can find a vector B in the subspace that is orthogonal to all the data points. And so this is going to be a bad situation for us. The good situation is when this CX mean is large. You will see that once I present the results. So I'm just motivating these concepts for now. All right, so in other words, CX mean, what is CX mean? Is a measure of the distribution of the inliers. And what we want is, in order for the data to be well distributed in the subspace, we want this CX mean quantity to be large. Okay, so the better distributed the inliers, the larger CX mean. The second quantity is going to be a characterization of the outliers, and we'll have two characterizations. So the first one really, this is just the norm of the objective. So in fact, let's go back to the objective. The objective on the outlier term is O transpose B. So the subgradient of O transpose B with respect to B is really the sign of O transpose B times O. And so that's what you see here, the sign of O transpose B times O. And then this matrix, identity minus BB transpose, is just a projection. So it's the projection of the gradient onto the tangent space to the sphere. And the norm of that vector is what this eta O is. And we're going to try to find the vector with the largest such norm. And so again, if the data is, if the outliers are highly concentrated in one particular region, this number is going to be very large. Conversely, if the outliers are well distributed, then this number is going to be small. And as we will see in the theorems, we will want this number eta to be small. The better distributed the outliers, the smaller the eta. And finally, there is this third quantity, kappa, that similarly measures the variation of the outlier objective. What is the difference between the largest possible value minus the smallest possible value? And again, the same sort of behavior that I just mentioned occurs, where if the outliers are highly concentrated, the minimum and the maximum are about the same. And so, it's exactly the opposite. If the outliers are highly concentrated, you've got a good difference. And if they're well distributed, this is going to be small. Okay, so in fact, what is very interesting, and let me try to actually explain why this phenomena happens. What is very interesting is that, let me see if I can annotate here, is the following. If you think of this objective and you think about the continuous version of it, in the continuous version, you're going to have the integral of O transpose B, where O is just a vector now. So maybe I should have denoted that. Okay. And then you're going to integrate with respect to some measure on the sphere, and you've got to integrate this on the sphere. So it can be proven, and this is actually a calculus exercise of just integration on the sphere. You can prove that this term is actually a constant. And it's a constant that only depends on the ambient dimension. It's really the height. Actually, the best way to think about it is that if you've got a sphere, and now because of the L1 norm, you just take the absolute value, you are computing the average height of the sphere. And this average height is a quantity, it's a scalar, is C sub D. So all what I'm saying is that the outlier term, if the data is perfectly and uniformly distributed on the sphere, is actually a constant. And therefore is independent on B. And therefore the maximum and the minimum are the same. So that's why very well distributed means that you have a small kappa O. And why is that important? It is important because going back to the objective, right? The objective is the sum of two terms. And so if the outlier term is constant and doesn't depend on B, then you know you have better chances of finding your global minimum, because it's really it's like the outliers have no effect. So again, I repeat, the intuition is in the continuum, if I had infinitely many, if the outliers are distributed in the sphere, the outlier term is constant, and therefore I know that I'm going to get the global minimum. Okay, so that's exactly what some of these quantities are trying to capture, but there are discrete versions of them. And that's why this difference between the maximum value and the minimum value matters, and it should be 0 when the distribution is perfectly uniform. So with that in mind, this is our first result, which characterizes the distribution of the critical points of this objective. So what this lemma says is that if B is a critical point of this DPCP problem, then there are only two possibilities. Either it lies in the orthogonal complement to S, and the orthogonal complement to S is really where we want it to be, right? We're trying to find the true normal to the hyperplane. So a critical point is either the global minimum that I'm trying to find, or otherwise is far from the global minimum. So because it says that the angle theta from the critical point B to the normal vector is bigger than this theta sharp. And what is this theta sharp? Is the arc cosine. So again, you can see that if the number of inliers is small, right, you can immediately see that the number of inliers m and the number of inliers n will play a role. And ideally you want, right, if theta sharp is pi over 2, right, this means that either you're the global minimum or you are at 90 degrees from the global minimum, right? So that's going to be the good situation. So we want this arc cosine of these to be close to pi. And immediately you can see what is the effect of the quantities that I was talking about. The CX mean and the eta O show up here clearly. Specifically, you can begin thinking, well, what is the asymptotic behavior of these quantities? And so as CX mean increases, the data is going to be better distributed, and this theta sharp is going to get closer to pi over 2. As the eta O is in the numerator, so if it goes down, then that's going to be good. And that causes the theta sharp to go up and to get to pi over 2, which is what I was talking about. As mentioned before, you can actually show that this eta O is going to go to 0 when the outliers are perfectly distributed. And again, the CX mean quantity is exactly the height of the sphere, the integral that I was talking about in the continuous limit. Okay. So anyhow, lots of technical details, but what is the big message? The big message is that critical points can't be anywhere. They're either the global minimum that I'm after, or they're far from the global minimum. And how far they are, it is controlled exactly by these geometric quantities, CX mean and eta O, and also by the ratio between number of inliers and number of outliers. The next one is really the main theorem, and this is really a characterization of the global optimality. Now that we know where the critical points are, how do we get rid of the critical points that are not a global minimum? And so the theorem is a little bit stronger than before, right? If you go to the previous result, this arc cosine just requires the argument to be less than 1. Now we want that argument squared plus a second term to be less than 1. So if this quantity is less than 1, then any global solution to the DPCP problem must be orthogonal to the true subspace. So this essentially says that we have a good formulation for the problem. I've pretty much explained everything, but again, I want to just point out the out inliers n show up in the denominator. So the more inliers, the better. M the numerator. So again, this tells you that there is a bound on the outlier to inlier ratio that's going to show up here. Then the CX mean is in the denominator, and that measures how well distributed the inliers are. And the larger the CX mean, the better, which is what I claimed at the beginning of the presentation. The eta O and the kappa O quantities that measure the outliers, they're both in the numerator. And as you can see, the smaller they are, the better in order to satisfy the constraint of the theorem. And again, as we stated, these quantities actually provably go to 0 when the outlier ratio is fixed, and then you let, say, n or m go to infinity. Okay, so therefore, what this tells you, it kind of begins suggesting that this theorem actually should hold with high probability if the outlier to inlier ratio is fixed, and then I let the number of inliers go to infinity, for example. So that's exactly, I think, the goal of the second part, which is the probabilistic analysis. But maybe this is a good point to stop here now that I'm done with the geometric analysis, to see if there are any questions.
Yes, there are a few questions, Rene. So first, the one from Anto. So Anto, do you still want to ask? I guess this question may be a little bit clear.
Yeah, so I'm a new student in this field, and I was just wondering, at the very beginning of your slides, you said that the global minimum is orthogonal to the subspace. What does that mean, that the global minimum is orthogonal to the subspace?
Let me see. So B is a vector, and this B is the optimization variable. And so the global minimum is the vector B that minimizes the objective at the very beginning. So the global minimum being orthogonal to the subspace means that the vector B that I compute by solving the optimization problem is perpendicular to S. Therefore, it is orthogonal to every inlier point. Did that answer your question?
Yes, that makes sense. Thank you.
Okay, so thanks. So we have one more question from Boris.
Yes.
Hi, Rene. Just a question just about the name of your algorithm so that I can kind of imagine how it works if you have higher codimension hyperplanes and things like that. You know, I think what you're saying in part, and that's my question basically, is that, you know, if you have a high dimensional hyperplane, maybe it makes sense to use duality, you know, and pass some hyperplanes to their dual vectors. Yeah. And then, you know, the relative dimension becomes like 1 minus the relative dimension or something. And, you know, so, exactly. Okay, thanks, great.
So that is true. And so that's a very good and valid point. But in principle, you would think that you do that only for reasons of efficiency. But I think the point I was trying to make is that all of the theory for all of the previous low rank methods really worked and required that dimension to be small, that there was no method that would have guarantees in the high dimensional regime. And the second point is that, at least to the best of my knowledge, and I could be wrong here, but the formulation is non-convex. I've not been able to have a formulation that is convex for the high dimensional regime. So even though it would appear to be something as simple as, oh, we'll just work in the orthogonal complement and then everything else that we knew before would apply, that's actually not the case. Did that answer your question?
That you had, you know, on yeah. B being norm 1, that's your non-convexity practically.
Yes.
Okay, right. Thanks. That's a good point.
I'm too naive, but I would like to ask you about general question, more kind of philosophical questions regarding your high dimensional, subspace. Many numbers of the subspaces. Actually, what you mentioned about yours, advertise of your method. But one general question is, if you think, there are many components, then actually that means, the energy is distributed many subspaces. Then, do you have any sense of how we can interpret of the? Of course, if we have the very, concentrate, low rank of the subspace, then it's very easy to understand of what's going on in the domain of the data. But if we have the many different subspace, it's very difficult to still understand of what's going on. So do you have any sense of how we can interpret of this, dimensionality in terms of the subspace and the number of the subspace?
So insofar, I've not been speaking about the case where you have multiple subspaces. That being said, a trivial interpretation, say, of the case of 2 subspaces, is that you can consider the second subspace to be outliers to the first. And therefore, the methodology that I'm presenting here could be applicable in that I need to, I run the method and I'm going to estimate the first subspace. And then once I've done that, then I can estimate the second. And indeed, a lot of the theory that I won't be presenting today about multiple subspaces, that's the basic principle. But as I have already hinted to, the theorems that I've just presented say, oh, if the outliers are well distributed, if they're well distributed in the ambient sphere, then that's good. But as soon as you have 2 subspaces, and the second subspace, I'm thinking of it as outliers, then they're by definition not well distributed in the ambient space. And therefore, the situation becomes more delicate. And that's why, even though it's the same algorithm and it is applicable both to one subspace or two, the theoretical analysis of it is more delicate to handle the very degenerate distributions of outliers when you have multiple subspaces. But that's a great question, but I won't be covering it today.
Thank you.
All right, so let me move now to the second part of the talk, where we're going to try to do the probabilistic analysis. So this was the geometric condition. And as I already said, by and large, it required the input, the inliers to be well distributed and the outliers to be well distributed. And that was characterized based on geometric conditions. But a weakness, right, is I probably can't compute these quantities. Like, what is CX mean? Like, I would need to know the inliers to do that. What is kappa O and eta O? I would need to know the outliers to compute that. So the question is, what is the distribution of these quantities? So let's assume that the inliers are drawn uniformly at random from the subspace, but now the inliers are a unit norm inside that subspace. So in this particular case, we can show that the CX mean quantity concentrates around 1 over square root of d. Okay, so that's the first result. The second one is about the other two quantities, the eta O and the kappa O. Roughly speaking, forget about the ambient dimension for the time being, but these quantities needed to be sufficiently small in order for us to succeed, and the CX mean needed to be sufficiently large. So these quantities concentrate below 1 over square root of m, roughly, is what this is saying. And of course, the eta O scaling is a little bit worse because it has the square root of d in the denominator. So if you wanted to see that in pictures, so this is what you see. The x-axis here is the number of inliers. We are keeping here the outlier to inlier ratio fixed and just letting that number grow. That's what the x-axis is, changing from 0 to 10,000. And you see the behavior of kappa O in green and eta O in red. They're decreasing, and they're decreasing in this case below 2 over square root of m. The blue curve, on the other hand, is the distribution of the inliers. The larger, the better. And it shows that as you increase the number of inliers and outliers here, the CX mean grows, and it grows to the maximum value, which is this CD, which is the height of the sphere of dimension little d. Okay, so what is the beauty of this is that it allows us to get rid of these geometric quantities and substitute them by dimensions. And the dimensions is dimension of the subspace, dimension of the ambient space, number of inliers, and number of outliers. And so that's exactly what this main theorem on the probabilistic analysis shows. And it says that a global minimum to the DPCP problem must be orthogonal to the hyperplane. So it is the true that we are looking at, with high probability, decreasing with 1 over the number of inliers squared, provided that the number of outliers, m, so this is what you see here, is less than or equal to the squared of the number of outliers. Forget about the constant for the time being. And so this really says that you can tolerate a lot of outliers. You can tolerate up to the square of the number of inliers. And this is illustrated with this plot here at the bottom, where again, the x-axis is the number of inliers. The y-axis is the number of outliers. White means success, means that the global optimum is equal to the true normal. And black means failure. And you can see, right, the number of inliers is ranging from 0 to 800, but the number of outliers is growing much, much faster here. And the curve has the quadratic shape as predicted by the theorem. The bad news, maybe, and we really need to sharpen these results, is that the capital D shows up in the denominator. The rest of it is logarithmic. And so I think the capital D in the denominator is the major problem to fix moving forward. And so in comparing with all other methods that I mentioned earlier, or even some alternatives, you can see that state-of-the-art methods, all of them tolerated only linearly. So the number of outliers, m, was linear with the number of inliers, n. So this fact that we can go quadratic is a big deal. again, what we're sweeping under the rug here, but I want to emphasize, is not perfect yet because we have the capital D situation in the denominator, while, for example, the method on the left, the geodesic gradient descent, has the square root of D in the numerator. So there is a trade-off there to be studied. In the spirit of time, let me maybe skip this. I'll just present one slide. We've been able to extend the analysis to data with noise. Everything I said so far was the data is noiseless, but corrupted only by outliers, but the inliers are perfectly in the subspace. So you might wonder what happens with noise. And I'm gonna skip much of the details, but let me just focus on the bottom right here. What this says is that the B star of the same problem, by the way, we did not do any modification to the optimization, which is quite remarkable. So the same optimization problem also works with noise, and the B star is close to the true normal vector. The sign of the angle between the estimated B, or the global optimum, and the true B is less than or equal to something like the noise level. Think of the standard deviation of the noise, divided by 1 minus the outlier ratio. So in particular, if there is no noise, the global optimum is equal to the true normal, which was the previous result. Okay, and the type of theorem is essentially of the same flavor as before, that essentially you can tolerate a number of outliers that is on the square of the number of inliers. Let me skip this. I mean, this is the actual statement of the theorem, but let me skip it. Okay, so let me now move to the algorithms. So this was the very first algorithm that we tried, where we begin with the objective. The objective is an optimization problem on the sphere, and the non-convexity really comes from the sphere. So all we did was to linearize the constraint. So we begin with some initial value for B, in this case denoted by N0. We linearize the constraint. So instead of B transpose B is equal to 1, what we do is B transpose our current estimate of B is equal to 1. So that gives us a linear constraint on B now. And now, because we have an L1 objective subject to a linear constraint, that's a linear program. So now we can solve for B by solving a linear program. And if we do that, we're going to get a new solution, N1, that then we project onto the sphere. And then we continue. We linearize, solve the linear program, and project. And now we've got this sequence of linear programs to be solved. So does this recursion converge? If it does converge to the global minimum that I was trying to look for? And does it converge to the same global minimum as the DPCP problem? So the answer is yes. And it's even better. It actually converges in a finite number of iterations. Okay. And so therefore is a valid and well-defined method. Okay, so this was the second method that we tried. And this was just reweighted least squares. So instead of working with the L1 objective, the L1 objective is illustrated here. It's just the sum of dot products. There is a typo here. This should be xj for the jth data point. So then you just scaled the objective. You construct the square, divide the absolute value, and now you substitute. So essentially what you get is the sum of the squared of the distances now, instead of the sum of the distances, but you have a weight, and that weight depends on your previous guess of the estimated normal. So the reason we did this method is that now you've got a least squares problem, right? Even though it's non-convex, this is quadratic subject to a unit norm constraint. So you can solve this problem using the SVD. And therefore, this leads to an iterative, the iterative reweighted least squares is like at every iteration you do the SVD and then you reweight your data and you keep going. So this is a classical and well-known method. And we expected this to be very, very fast relative to solving a sequence of linear programs. But we don't have, we've not been able to have, maybe we stopped for what I'm going to tell you next, but we don't have theoretical guarantees. But I think this should be doable. We should be able to prove that this converges to the global minimum, but we don't have the result yet. Okay, so what we actually do, is this projected subgradient descent method. And so in the projected subgradient descent, it builds on the previous theory. It's like, well, if we can get a good initialization, then we do a local search algorithm to find a critical point. So let me actually tell you what is that. All we do is that we take this non-smooth objective. We can compute an element of the subgradient. Then we do a subgradient descent step. That's going to get us out of the sphere. And then we project. And we repeat this process, compute the subgradient, move, project. So what are the key questions? So a trivial method, right? Is just almost like gradient descent and projection. So how do you choose the step size? Does this converge? I mean, the main challenge is that the problem is non-convex, and if it does converge, where? Those were the theoretical questions. So we've been able to prove that the spectral initialization, which is really the SVD solution that was supposed to not be robust, it's a good initialization in the sense that it gets us into the ballpark. And then we do the projected subgradient descent at dates. It's exactly what this is exactly what I said, but in equations, compute an element of the subgradient. So the only thing is the mu k here is the step size. So how do we choose it? So the key insight from JHU's work is to choose the step size in a piecewise geometrically decreasing rate. So mu0 is the initial step. Beta is a rate of decrease. And what we do, and this is illustrated, is just look at the green curve. So the rate is constant for k0 iterations, and then you multiply it by beta, which is less than 1. And then it's constant for k iterations, and then you decrease it, and you keep decreasing it. And what the blue curve illustrates is the objective. So the objective is provably bounded, I think, between this piecewise geometric rate and these upper bounds that are shown. And the upper bounds, they're all functions just of the rate and of the initialization. So specifically, this is the theorem. If the initial angle between the B vector and the true normal to the subspace is smaller than this theta sharp, and the theta sharp was the same as the one that appeared in the theorem for critical points. And remember that theta sharp is going to pi over 2. So it's really, this is a very mild constraint on the initialization. Then piecewise, the projected subgradient method has a piecewise linear convergence rate for the tangent of the angle theta k between your estimate at iteration k and the true normal to the subspace. And this is what the theorem says, I think. So in summary, the sequence of linear programs, we had very nice theory, but it was not very scalable. Iterative reweighted least squares, we do not have theory, but it was much more scalable. And this projected subgradient method is actually the simplest, the most scalable, and we probably have the best convergence results for it. So this is illustrated here in this figure. The plot on the left, the x-axis is the number of iterations. The plot on the right is time, okay? And you can clearly see if you look at the green curve, and the green curve is the sequence of linear programs, it just requires very few iterations, but every iteration is a linear program, and so it's very costly. So that's why in terms of time, the green is on the far right. And I guess the comparison of various different methods, but I think what I'm trying to advocate is that the red and the blue are kind of the winning methods. And the red is projected subgradient method, where the rate is via backtracking. And the blue is the one that I just presented, where you have this piecewise geometrically diminishing step size. Okay. Also note the, what color is this? Purple, I guess, or with a constant rate, it does not work, right? You can see it's much worse. So this key insight of properly selecting the step size is what gets us the convergence. Okay, so I'm not going to repeat the experiments, the synthetic experiments. Let me now show you this data set. This is the Kitty data set. This is lots of data that was taken by a car, 3D point clouds, images. The goal here is to estimate the ground plane from point cloud data. you see at the top right the data, and the blue points are on the ground plane, and the red points are everywhere else. So you've got really a very large number of outliers. Here, 53% of the points, more than half, are outliers. And so this data comes annotated, so we know the ground truth, the blue points. And now what you can do is just run DPCP or any other algorithm on this 3D point cloud. And the algorithm is going to tell you which ones are inliers and which ones are outliers. And then you can also estimate the ground plane and compare it with the inertial measurements of the car. Okay, this is to show you a little bit the data. And you do this for lots of videos. Okay. So this is showing the results on over 100,000 data points, and the F1 measure is a measure of the agreement for the detection of inliers, like what is not exactly what percentage of the inliers are properly detected, but I think you're familiar, right? There is the false positives, false negatives, so you get the F1 measure out of it. And I think it's to demonstrate that, you know, some, like the beautiful method that we loved from standard, the outlier pursuit method does not do very well. And again, is in this particular case is because the data is not low rank enough for the classical convex methods to work. So going to the dual and solving these non-convex problems efficiently pays a lot here. This is just to show you. We have done this for various data sets. So RANSAC, the oldest method, actually remains very competitive for these very low dimensional problems like planes. But the DPCP is competitive. It's the same ballpark. To summarize, what I've presented is a non-convex L1 formulation for robust subspace learning. It extends to multiple subspaces, but I did not present that. The method is provably correct. It performs very well in practice. We've been able to show that it can tolerate as many as the square of the number of outliers. So you can learn subspaces with a small fraction of with most of the data being outliers, actually. And we've been able to propose a super simple algorithm, compute your gradient and project and iterate. And the clever insight is really properly selecting the learning rate for the algorithm, and you get piecewise linear convergence. And well, I did not emphasize this because our goal was really to make this work in high relative dimensions, but the method works in both cases. I didn't talk about it, but obviously this can be extended to multiple normals at a time. Well, that's it. I think, let me just thank my collaborators. I think Manolis Tsakiris was the person who started working on this in the lab, and he was the one who did all of the initial geometric theory as well as the initial algorithms like the linear programming. Jihui Zhu was a postdoc in the lab at the time, and he did all of the nicer geometric theory, more easily interpretable, as well as the probabilistic analysis, as well as the new algorithms. And Tianyu Ding is the current student, and he is the one who is working on the extensions to noise that I presented very briefly, as well as extensions to subspaces of higher codimension, as well as the extensions to multiple subspaces. And everything was done in collaboration with Daniel Robinson. Thank you. Questions?
Okay, so thank you, Rene, for the wonderful talk. We do have few questions. First one may be so bored, so do you want to unmute yourself and ask?
Yeah, sure. Very interesting talk. Thank you, Rene. I have a question about your probabilistic theorem with the bound, you know, that you get capital N squared on the right-hand side. Yeah. I saw that there was also a little d in addition to the big D in the denominator.
Yes.
So you know, the ratio of capital N to little d could itself be a constant, or you know, that's an interesting kind of ratio to think about. So you know, I was just wondering if you had a comment about how to think about the ratio of big N to little d, That you're kind of having like a lot more data than you need to specify the hyperplane or something like that.
Yes. So a first initial comment is that in the hyperplane case, the little d is capital D minus 1. So roughly speaking, the denominator would be perhaps even d squared if you don't have enough data points. The dependence on capital D comes from the concentration bound for the eta O here. That square root of D is the one that is sort of killing us in this analysis, and trying to get rid of that square root of D is the gist of the crux. So back to your question. The reason why it works so well for all the geometric problems we've tried is because when you think about fitting point clouds, capital D is 3. When you think about the other geometric problems in vision that I didn't get to mention, like homographies, capital D is 9. And 3-view geometry, capital D is 27. Maybe Ziwi will be able to comment more as to whether he was able to get it to work reliably for larger D, and in particular, what was the trade-off between N and D? Ziwi?
Yeah, I think here from this result we kind of like think D is fixed and we let N increase or somehow. So we have this like bond. So in the algorithm we have D and capital D, they both work pretty well.
I see.
So I think so the ratio between capital N and little d, it is we will not feel it as a constant. So we mainly try to increase the capital N here.
Okay, I see. I understand. That's fair.
Nice. Okay, so we have question from team, but does anyone else from the audience have any questions? Okay, so Anto has one more question, so can you ask?
Again, this might be a stupid question, but I'm just wondering, isn't the fact that M can be greater than N counterintuitive? Wouldn't that mean you have more outliers than you have inliers, and then wouldn't the outliers become the inliers? Sorry, just a simple thing I wanted to clarify.
Let me try to go back to some of the motivations. Where was that picture that I wanted to show you? Okay, so first of all, the very last point, wouldn't, if the number of outliers is so large, wouldn't it be the other way around? So no, the reason is we are assuming that there is a subspace and the inliers are the points in the subspace. The outliers is everything else. And so regardless of what the number of inliers and the number of outliers are, there is always the notion that the inliers are the points that are in the subspace. And that therefore, the outliers are generic in that they don't form another subspace themselves, okay? That would, second, you would wonder, well, and in fact, this is very commonly found in statistics, that people tend to want the number of outliers to be small. But if you really work in computer vision and you do matching of two images, you will see that when trying to match a corner of a window in one image to a corner of a window in the other image, there are so many other windows that most of your candidate matches would be completely wrong. So in most of these geometric problems in vision, most of the matches are wrong, and only very few of them are the right ones. And therefore, developing algorithms for cases where the number of inliers is significantly smaller than the number of outliers. It's actually very common in real world data.
Okay, thank you. That was a very good explanation. Thank you.
Okay, so Qin, do you want to ask?
Yes. Thanks, Rene, for the great talk. So my first question is, so is initialization for the analysis and the algorithm critical? I mean, is there any other bad local minimizers outside the initialization region that my second question is that for the projected subgradient descent methods, why the step size is choosing like a piecewise geometrically shrinking? Is there any reasons for this? And my third is that can this analysis be methods to extend it to like multiple subspaces? Thanks.
Yes. So let me take the first and the last, and we will take the second, I think. So initialization. There was this lemma in the paper that if the initialization is, there is this lemma that there is no critical point in the middle region. So the critical points are either global minima or very far. And that leaves that theta sharp, means that critical points need to be beyond that theta sharp. Okay. So what is the initialization? The initialization was here. Do spectral initialization. And I think the theorem is that with high probability, spectral initialization is in the right region. Moreover, this region, the value of theta sharp goes asymptotically to pi over 2. So initialization is generally, fortunately, this is not usually the case, but for this problem, is generally easy, and it's not a big issue. The second one is, the third question was whether the analysis extends to multiple subspaces. The answer is yes. In the case of multiple subspaces, the second, third, fourth, fifth, all other subspaces become the outliers. And the goal is to be able to return what we call the dominant subspace. And we have a couple of papers proving that